11.1, a constant ratio. So hopefully that ratio will get you thinking about what we talked about in the do now. We did at the end of 10.3, where we took the length of an arc and divided it by its radius. So we're going to look out for that ratio here. Diego and Lynn are looking at two circles. Diego says, it seems like for a given central angle, so here they've got theta as their given central angle, the arc length is proportional to the radius. That is, the ratio L over R has the same value as the ratio capital L over capital R because they have the same central angle measure. Can we prove that is true? So basically we've got this lowercase l over R, so the smaller arc length over the smaller radius. They want to know, is it going to be equal, have the same value to our larger arc length over our larger radius? And hopefully this idea of comparing ratios and having them be equivalent makes you think of our similarity unit, our first unit of the year. Okay, so Lynn says the big circle is a dilation of the small circle. If k is the scale factor, then the larger radius is equal to the scale factor times the smaller radius. Diego says the arc length in the small circle is, and he gives the variable for the arc length, theta over 360 times 2 pi r, where there's the smaller radius. In the large circle, it's capital L equals theta over 360 times 2 pi capital R, the larger arc length, the larger radius. We can rewrite this as capital L equals theta over 360 times 2 pi rk, so L equals KL. There's a lot going on there. We're going to try and break that down a little bit simpler, because that's a lot to take all at once. Lynn says, okay, here's how I can show that smaller L over smaller r and capital L over capital R are equivalent. All right. How does Lynn know that the big circle is a dilation of the small circle? Well, this sort of comes from the fact that all circles are similar. No matter how you draw a circle, it will be in proportion with any other circle. And why is this? Well, a circle is defined as the distance from a central point by its radius out over here. Every single point on the circle is a distance of r away from the center. Every single point on the circumference here is a distance capital R from the center. So there's just one length in the entire shape. Only one length that we can measure, and if I just multiply my scale factor by the smaller length, I get the larger one. All circles are 360 degrees around, right? Those angles are the same. Another shape where this idea is seen also is a square, right? All squares, we can say, are similar. All squares are dilations of each other. Because all the sides are proportional, I can multiply one of the sides by a number, effectively multiplying all sides by that same scale factor. The angles are also all the same, which is another reason we can say they're similar. A shape where this doesn't really work is a rectangle, right? I can have two rectangles. Right, these are both rectangles, but they are not similar. They are different shapes. This one is wider. The proportion is not the same between all sides. No matter what, this is a square, right? If I have 3, 3, and 3, 3 over 3 is equal to 1. Let's say I have a bigger square. This is 5, 5, 5, 5. 5 over 5 is still equal to 1. So the factor between the sides is always the same. Might not be the case in a rectangle. So because, a circle is really defined by this one measurement, that scale factor is going to be the same. It's going to create a similar figure. You'll learn about some circular shapes that are not that case. Think of like an oval. Right? If this is the center of my oval, the distance from here to there is not going to be the same as the distance from the center to here. So not all ovals are similar. Because the radius is always the same all the way around the circle, we really have similar shapes. So why does he know this? All circles are similar. Right? You can't really distort a circle, then it doesn't become a circle. If it's stretched out, it's like an oval or an ellipse. All circles you pull the radius away the same amount from every part on the circle, so it's something that's consistent throughout. That's sort of an abstract idea. All right, 2. How does Lin know that capital R equals K times R? Well, technically, he doesn't know exactly that. We're assuming that K is going from smaller to larger, that scale factor. Because remember, you can also have a scale factor that goes from larger to smaller. So we're assuming that K is greater than 1. But why does that make sense, assuming that that's true? Well, if R is my small radius, I'm going to multiply the small radius by the scale factor to get up there. Let's say we had radius of 1, radius of 3. Radius of 1, radius of 3. I'm going to multiply this by 3 to get to that radius. That's my scale factor. R is larger radius. Lowercase r is smaller radius. Why could Diego write that the length of the arc is equal to 360, theta over 360 times 2 pi r? I mean, we've seen that formula, a dozen times now. That's our formula for arc length. Theta is the central angle. That holds true here. Lowercase l is the length of the arc. That's what we always use. And lowercase r is the length of the radius. So they've substituted all values in properly and for that formula. All right, so when Diego says that the large arc is equal to the scale factor times L, what does that mean in words? What he's trying to say is that if you multiply the arc length by the scale factor, you'll get the larger arc. So really breaking it down, if you want to write it, K times lowercase l equals L, because that's the order that I'm going to read it in. Scale factor times small arc length is equal to the large arc length. Why could Diego say that uppercase L is equal to the scale factor times lowercase l? Well, we talked about in the previous lesson about one-dimensional and two-dimensional scales, right? So when we're talking about circumference and radii, those are one-dimensional measurements. So we're going to multiply by just the scale factor. If we were talking about areas of the sector, we'd be multiplying by the scale factor squared. But why does it really make sense algebraically? Well, we know that our formula for L is really theta over 360 times 2 times pi times uppercase r. And we know from earlier in the problem that uppercase r is really the same as K times lowercase r, because we're multiplying the scale factor of our smaller circle. So really I could say that this right side is equal to theta over 360 times 2 times pi times L r, or I'm sorry, KR, sorry, the scale factor is K. All right, and now using our commutative law of multiplication, I'm going to switch my order. I'm going to put K in the front here. So really I can write this as K times theta over 360 times 2 times pi times r. Well, where have we seen this expression before? Theta over 360 times 2 times pi times r. Well, that's exactly right, this, right? That's where that lowercase l we said equal to earlier. So in reality, we're saying L is equal to K times lowercase l, which is exactly what they have right there. Right, now we use substitution. Or I guess, yeah, no, substitution would be the correct word for that, not transitive. Okay. how can Lin show that L over R is equal to L over R? Well, that's a tough one, right? All right. So how do we want to show this? Well, if we look at number 2, right, we said R is equal to K times R, right? And now over here we've got L is equal to K times L. Well, both of these equations have something in common, right? They have that letter K. So let's get K alone in both equations. So I get R over R equals K. And on this side we can get L over L equals K by dividing both sides by that lowercase l. All right, well now I have two equations that are both equal to the same variable. They're both equal to K. So what property can I use here? Hopefully you said the transitive property. All right, so I can say R over R is equal to K. I'm sorry, L over L. Well, at first glance, this does not look like exactly what we wanted here before. So I'm going to cross multiply really quick. So I get R times L is equal to lowercase r times uppercase L. I want uppercase L to be in a numerator. So I'm going to divide both sides by r here. That gets rid of the r on that side, and I'm just left with L equal to R times L for uppercase R. Well, look here. I want uppercase L all by itself, and I've got an R over on this side, so I want to get rid of that R. I'm going to divide both sides by lowercase r. It's going to cancel out with that. And then on my left side, I'll have lowercase l over lowercase r. And here I just have L over R. So that's a lot of complex algebra. It's okay if you don't think you can replicate that, you don't have to. But really what we're trying to show here is that the ratio between an arc length and a radius in two different circles, as long as that central angle is the same, that ratio will always be equivalent. But theta has to be the same. That's the only caveat. All right, that's all for 11.2.